Alright, this is sound video for Physics 1, Part 2. And we left off with going into air columns, which can be one sound source for sound itself. Other sound sources, as you can see here, piano, violin, guitars, they all use what's called vibrating strings. Saxophones use a vibrating reed. Flute will use air columns, like looking into, our voice use vocal cords. And so all these sources have things that involve vibrations that are in contact with the air, and the sound travels outwards from them. So when we're looking at air columns, it's very similar to what we saw in solar harmonic motion when we're dealing with standing waves. In the same way, we have what's called nodes, which is a point of zero displacement, and we have antinodes, which is a point of maximum displacement. And if we have a balance system, the wave that we have for sound will reflect off the one end and reflect in vertically back towards the beginning, and it'll just continue. So for air columns, the fundamental frequency here, or the fundamental harmonic, basically, the wavelength is equal to twice the length. Okay, so again, if you have a bound system, right, you'll have 1/2 of a wavelength within that bound system, and that's your fundamental. Right, an overtone will have well, before I get into the overtone, your frequency of this fundamental is going to be equal to the speed of the wave over 2 times L. The overtone, or the next harmonics, are going to be equal to N times the fundamental frequency. So NV over 2L. Okay, and so, like, for instance, when N equals 1, you'll have your full wavelength and one node in between the two spots. We're going to look at this in a couple ways. We're going to look at it as displacement of air, and we're going to look at it as in change in pressure. So if we start with an air column here, and in this case, unlike the bound system, we're going to have this air column open on both ends. So it's basically like a tube like this, kind of like, I guess you can say even a straw. And the air can, go in and move through. It can come out either way. Right. So with that, you'll have antinodes on both ends of this, because the air can move in and out from this. So it's going to be a maximum displacement here. The air is free to move. There has to be at least one node for it to be the fundamental, and that node is going to be at the center. If we look at change in air pressure, the pressure does not change on the outside, and so you have the nodes on the outside instead And so there must be one antinode to be a standing wave, so that would be on the inside. And I think, let me see if I have a picture of this. Yes, I do. It's on the next page. Right, so here's what it'll look like with the pressure, where you have the antinode in the inside and you have nodes on the outside. Okay, either way, we're looking at all the same equations. We're looking at the wavelength being equal to 2 times the length. So this is a half of a wavelength, and this is a half of a wavelength. And so our frequency for the fundamental is still V equals 2L. And then when we go and we add more nodes, basically one at a time, you end up here. Now you have the 2 nodes on the ends for the air pressure and 1 node in the middle, so you get the full wavelength here. Or in this case, it's opposite. You have still the antinodes on the outside, but instead of 1 node in the middle, you have 2 nodes in the middle, and you get a full wavelength. This will actually look more like a cosine wave here. And then we go to 3, and then so we add 1 more node, and this becomes one wavelength. Let me get this, 1 wavelength and then a half a wavelength. And same thing here, we add now another node in the middle. So now instead of just 1 in the middle, we have 2 in the middle, and you get 1 whole wavelength and then a half a wavelength. And so it follows the same equations we had here, just as we had with the standing wave. Now, where things change, I'm going to make this adjustment a little bit so we can see it better. With the standing wave, with the tube closed on one end. So here we're not looking at both ends open, but where maybe there's a cap on one end. You still have to have 1 node and 1 antinode. So on the end that's closed, you're going to have a node. And the end that's open, you're going to have a antinode for when you are dealing with displacement of air. So the air here is free to move, and so that's why it's an antinode. Or here it's not free to move, it's enclosed, and that's why it's a node. This actually is 1/4 of a wavelength. Right, think about it, this has went up, hasn't came back down, and hasn't really came back to beginning either. So this is 1/4 of the wavelength. And so here our wavelength is 4 times the length. So we would need 4 lengths of this tube before we get the whole wavelength involved. And so our velocity now is, our frequency now is velocity over 4 times L. And then if we add in this case, another node, so now instead of 1 node on the end, there's 1 node before you get to the second maximum. And so this would be half of a wavelength and then another 1/4. So that's 3/4 of the wavelength. So the wavelength itself would be 4/3 of the length of the tube. And then we go again, we add another node, and we get 1 whole wavelength plus 1/4. So the wavelength is 4/5 of the length of the tube. One thing to notice with these is we're skipping the even harmonics here, and then that's what happens with this. We don't have F2, we don't have F4. We have F1, which is your fundamental, F3, which is your third harmonic, and then F5, which is your fifth harmonic. And the same thing works with the air pressure, and it's kind of just reversed. You have a node where the pressure cannot change, and then where the pressure can change, you have a antinode. And so we add more nodes as we move through, and the same thing happens. The wavelengths, basically we skip the second and fourth harmonic, and we'll skip the sixth harmonic and eighth harmonic all the way down with the way that this works. Alright, so let's do a couple examples. Alright, so we have an organ pipe that is 116 centimeters long. Determine the fundamental and the first three audible overtones if the pipe is open at both ends. So this is open at both ends. I don't really have to draw it, I guess, but I will. So the first thing we want is the frequency 1, and then we'll want frequency 2, and then frequency 3. And these frequencies will be V over 2L, and then technically NV over 2L, and then NV over 2L, which becomes N times that fundamental for both of these. And in this case, it'll be 2 times that first frequency and then 3 times that first frequency. Alright, so once we get the first frequency, then we can just multiply it to get the next 2. Now, we don't know what V is yet, so we gotta find V. So V is going to be the speed of sound. Right, and we know it doesn't tell us the temperature, so what we're going to use is we're going to assume about 20 degrees, and we're going to say the speed of sound is 343 meters per second. Right, so the first one, 343 over 2 times 1 point, let me change that to meters, 1.16 meters. And we get 147.8 hertz. Right, so this would be 2 times 147.8 hertz. So F2, which I'm going to write down here, F2 is then 443.5. I'm sorry. I wrote the wrong number. 295.7 hertz. And then F3 will be 3 times 147.8, which is 443.5 hertz. And so the first 3 overtones, so we'll do one more. So F4 is 4 times 147.8, which is 591.4 hertz. Alright, so the next thing we're going to look at is when we close one end. And so when we close one end, we don't have the even harmonics. So what we're going to look at is we're going to find F1, and then we'll find F3, F5, and F7. Okay, so F1 is going to be V over 4L. Since this is with one end closed, it takes 4 times the wavelength to get, 4 times the length to get the wavelength. And that would be 343 over 4 times 1.16, which is 73.9 hertz. And then each one after these is just n times our frequency of 1. So 3 times the frequency of 1 equals 3 times 73.9, which is 221.8 hertz. And then 5 times the frequency of 1, which is 5 times 73.9, which is 369.6 hertz. And the last one, 7 times the frequency of 1, which is 7 times 73.9, which comes out to be 517.5 hertz. Right, so we end up with different frequencies with the tube open than with the tube closed. You know, beyond this, we're getting into the science of music, which I'm not big on. Alright, so the next thing we're going to get into, the last two things we're going to do are beats, and you can see Doppler effect is going to be the next one, which I do like Doppler effect. Beats, we're not going to get a whole lot into detail, just want to mention it because it deals with some things that would definitely be brought up in Physics 2. For beats, you have constructive interference, you have destructive interference. So constructive is when two sounds come together that are in phase with one another, and so they reinforce each other and you get amplified sound. Destructive is when two sounds are out of phase, and so they end up canceling each other out. So one sound cancels out the other one. They actually have special headphones made to cancel out the sound of jackhammers. So people using jackhammers don't have to listen to the horrible sound from it. What we have is called beat frequencies, and this is how often two sounds have constructive interference. How often do they reinforce each other? So if we have two guitars that are brought together, one has a frequency of 380 hertz, and the other guitar has a frequency of 390 hertz. How many beats will be heard in 10 seconds? So to find this, we have to look at first the difference of the beats. Which is 10 hertz. I started writing hertz before I wrote the number. 10 hertz. And then we're going to look at what that means. What 10 hertz is equal to 10 vibrations in 1 second. So we're going to multiply this by 10. So multiply the top and the bottom by 10, which actually multiplies it by 1. And so you get 100 vibrations in 10 seconds. And so you will hear 100 beats in 10 seconds based on this. Right. So next is the Doppler effect. And I always think this is kind of cool. I like to kind of go through this, one of the main things is you're going to be looking at some different equations depending on the situation. But the equations do all look very similar, so they're sometimes easier to remember. There's tricks to remembering these, which one means which. Right, and so the Doppler effect, this is dealing with when you have a source or the sound is moving away from the observer, or the observer is moving away from the source of the sound. So if we think about this, when this fire truck's at rest but the siren's going off, you can have a person behind it or a person in front of it, and they're hearing the sound and they're seeing the wave, not seeing it, but they're experiencing the wavelengths, and it stays the same as the sound goes out through, and it stays the same for both sides. When this fire truck starts to move, because it's moving forward, each next source of the sound happens closer, and so these wavelengths decrease. Whereas here, each source of the sound now is moving farther apart, so these wavelengths actually increase as this thing moves farther apart, and so you hear a different wavelength when it's moving. And so we're going to look at first the moving source. Right, so just like that fire truck, we're going to look at a moving source here. Right, so here's the source, and in this part here, A, this source is fixed, it stays here, and so this distance is some wavelength that we'll call lambda. Now when that source moves to point 2 here, you now get a wavelength that is different, and for this one it's shorter than this wavelength since it's moved closer. The distance between this source and the distance between the sources is the velocity of this source. How fast was this object moving from point 1 to point 2 times the time it takes to go from point 1 to point 2, and you get the distance of this source here, the distance the source moves basically. And then you have the distance that was fixed, and so this wavelength is going to be the wavelength or the distance that was fixed at the beginning minus the distance that this object moved. Right, so now this wave doesn't have to go as far, or the sound doesn't have to go as far because you moved closer. Right, so when moving closer, the observer has a higher frequency because you're getting shorter distances that these waves have to actually move, and so you're getting shorter wavelengths. Alright, so we can take this equation, and I'm substituting in for the source of the distance, the velocity of the source times time. And so if I solve this for the time, that's just going to be the wavelength divided by the velocity of the sound. Alright, so this time can be found by the time it takes for the sound to move one wavelength over its velocity. And so we can plug that in for this time here into this equation. So we're plugging this into, well, I can't write on this, but we're plugging this into that, and this equation into that equation. And so we have that this new wavelength is equal to the original wavelength minus the velocity of the source times the new wavelength, oh, I'm sorry, the original wavelength over the velocity of the sound. And we can factor out the wavelength, and so we get one wavelength times 1 minus v source over v sound. So now, if we look at the new frequency that we're going to have, this is going to be equal to the velocity of the sound over the new wavelength. Well, we found the new wavelength, that's going to be what this is. And so we have the wavelength, velocity of the sound over the wavelength times 1 minus v source over v sound. Well, the velocity of the sound over the wavelength is the original frequency. So our new frequency is actually just the frequency originally over 1 minus v source over v sound. So I'm going to write that up here actually. This is probably the equation to remember or to have written down for this part of it. Again, this is moving source, and this is source moving towards observer. Okay, so now we're going to look at the moving source. And the source moving away from observer. It has a very similar idea, but instead of the distances subtracting, they're going to add. So the d distance the source has moved plus the original distance the wave had to travel is going to be the new distance that the new wave has to travel. And so you get an increase in wavelength or a longer wavelength, which means you'll get a lower frequency. Right, and so the observer is detecting less wavefronts passing through every second as the source moves away from him until there's no wavefronts getting to him. And so we can look at that very similar algebra. Wavelength is the original wavelength plus v times the source times time. That time is still the wavelength over v times the sound, or v of the sound, velocity of the sound. And so we substitute that into that first equation. We have the new wavelength is the original plus v source over v sound times the original wavelength. Again, we factor out the original wavelength, and we get 1 plus v source over v sound times the original wavelength is our new wavelength. And then again, very similar frequency, new frequency is v sound over this new wavelength, which is now the old wavelength times 1 plus v source over v sound. And so in a similar way, this v sound over the old wavelength is the old frequency. And so the equation for this new frequency looks very similar. Old frequency over 1 plus v source over v sound. And really it's just a matter of, well, if it's moving towards, you have a minus sign. If it's moving away, you have a negative sign, or a positive sign, sorry. So, I mean, you're looking at pretty much one equation here. Now, if we look at the moving observer, or so they say this cause beeping, making, let me see here, that's the observer. So they're driving, they're moving, and there's a sound, maybe it's a siren somewhere, and so they're moving towards it. The way it works is you will have this frequency. So and it's going to be equal to this velocity of the kind of the difference between the sound and the observer's velocity. Well, not the difference, but the combination of sound and observer. And that combination times your frequency and wavelength will, and divided by your wavelength, will be this new frequency, which I should have this here. That's the new frequency. I don't know, I must have just missed that little thing to make it new. Oops, I don't need that. Alright. And so, if we split this up, this V sound over V sound would be 1. This V observer over V sound will be what we get here, times the original frequency will give us our new frequency. And then a very similar method, again, just like over here, the sign is just the difference between these two equations. So very similar way, if we have a moving observer and it's moving towards, you have the new frequency equaling 1 plus V observer over V sound times the old frequency. And then moving observer moving away, the only thing that changes is your negative sign. Alright, so we have 4 equations depending on what sound or velocity is moving. We're not going to go any further into that. We're not going to deal with both of them moving. This is enough for now. Alright, so this ends the few videos on sound and a few videos on simple harmonic motion and vibrations. What we're going to get into next is kinetic theory and heat and thermodynamics before the end of the semester. Alright, I will see you in the next chapters.